is 183.
122 and 183. Nice. So to reiterate what you did there, you essentially realized, okay, rate of change, first difference, not constant, right? It went 11, 13, 19, 29, and so on and so forth. You went to the second difference, still not constant, but now you realize the difference was just 4. And so at the third difference, it was constant. What kind, so this means it must be some type of polynomial to represent this. What kind of polynomial would have a constant third difference? Don't overthink it. We're overthinking it. Yeah, it is a cubic, Rickle Chickle. It is a cubic. If the third difference is constant, this is going to be a cubic. So way to go. All right, we'll talk more about those, I think, tomorrow. But in the meantime, I heard y'all wanted to talk about some series. So we're going to focus mostly on geometric series. Arithmetic series are a little bit easier to deal with. I think, oh, I'm cutting out. I'm so sorry. Sometimes my internet is trash. Arithmetic series are a little bit easier to deal with. I think that we feel confident in that. Does anyone want to remind me how we could find the sum of an arithmetic series? Or maybe we don't know. So like if my series was like 1, 3, 5, 7, 9, and 101. What would you guys do? How would you find the sum of that series or sequence, I guess? What are we feeling? How would we go about that? Or do we know how to go about that? Maybe that's a whole other thing. Maybe we forget how to go about that. Make pairs? What do you mean by make pairs?
You would have to do like 101 plus 1, and then like 99 plus 3, and then like you divide that by the total amount, and then multiply it by like the amount of pairs.
Yeah, so we realize essentially we take the first term, the last term, add them up, and then multiply by n divided by 2, because that'll tell us how many pairs we have. The only thing we'd have to do in this is figure out like what term is 101, right? Like if it just said like the 50th term is blank, then it'd be a lot easier. But here we have to essentially figure out what term 101 is. Okay, now technically you guys learned this back in Math 1, but I know it's been a hot minute since you've been dealing with this. But someone tell me, what is the difference? Does anyone know what the difference is between sequence and series? What is the difference between sequence and series? What do we know? We're slow on the chat today. Ananya, what's the difference between a sequence and a series?
I might be wrong, but like
Yeah.
a sequence is just the list of numbers, and then the series is the sum.
Yeah, that's exactly right. A sequence is the listed number, a series is a sum. Okay, so in a sequence, we're literally just going to be listing them off. So it would be like 1, 3, 5, 7, 9, dot, 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 right? Whereas a series is literally 1 plus 3 plus 5 plus 7 plus 9. So I wanted to talk about specifically geometric series because I think that's maybe the harder one to deal with. And this is here saying that you're going to start off with your starting term. A sub 1 is the starting term. And between each one, you're going to multiply by some ratio, right? So we've seen this a lot of times, maybe like 3, 6, 12, 24, 48, right? Here we know that in this case, our starting term is 3 and our ratio would be 2. And we know each term is a times r to the k, where k starts at 0 and goes up to n minus 1. You essentially multiply by 1 less than the ratio. If it is a finite series, meaning that it has some type of end, right? We're finding the sum of the first 50 terms, first 100 terms, and we can always find the sum of a finite geometric series. But what we would do is we multiply it like this. We would say it's the first term times 1 minus r to the n over 1 minus r, where n is the number of terms and r is that ratio. Okay, questions, comments, concerns here? Now this also, this is a Riemann sum. This is sometimes also called a sigma. This means essentially to sum up the terms. You starting at term 0 and you finish at term, that's like the final term. That's your start, and then this is your final. Questions, comments there, or do we feel okay about it? I mean, obviously I'm going to give you some as well. All right, let's try some out. So I would like you to find the sum of the first 10 terms here. Some of the first 10 terms. Now, if you wanted to, you could also list this out, right? But we're assuming you're not going to do that. So this is the sum of our first 10 terms. Take a minute and see if you can get these two. So in the first one, we realize our first term is 6. Right, so if we wanted to list this out, we could also list this out and go like, all right, 6, then we'd get 2, then 2/3, then we would get 2/9, then we would get 2/27, and then something. We could keep doing that, right? But again, this would be the sequence. If we want the series, we would just add these in between. So our first term is 6 times 1 minus 1/3 to the what? What is our power here that we're going to raise it to? Is it to the 11th? Let's look back. So we realize that if this is to the n minus 1 power, we're doing 1 minus r to the n. So according to that, we would do this to the 11th. Is that correct? That's assuming that we're essentially saying start with term 0. So this is term 0, and then we're going to be applying this a total of 10 times. Yeah, I did put n on the bottom. That's on me. I think yeah, because in this formula it deals with the k, right? So it kind of uses that other variable to say that's to the k and this is to the n minus 1. And then we do r to the n. I mean, it's the same thing, right? You're essentially saying it's 1 less than the power. So I would say that this would be to the 11th. And then we're doing 1 minus 1/3. So this gives us 6 times 1 minus 1/3 to the 11th, all over 2/3. So we could get that, and that would look like what? 20. Yeah, I can multiply. That would be 9 times 1 minus 1/3 to the 11th. Now let's talk about what's 1 minus 1/3 to the 11th. No, we don't know we don't have a calculator. Oh man, if only we had a calculator where we could put in 1 minus 1/3 to 11. How did I get 9? I did 6 times 3/2 because I know there's a 2/2 in the bottom. If you go back, it's 1 minus r, and so 1 minus 1/3 would give us 2/3, so I multiply by the reciprocal. It's like 0.999999943, right? And so that's really close to 1. So this is very close to 9. It's like a little bit less than 9. If we multiplied it out, we would get like real close. The answer, the calculator would tell you real close to 1. To the 11th. Yeah, I get 8.999999. What do we think? Do we agree, disagree, hate it, love it? It's the worst, it's the best, what?
Wait, where do you get the 11 from for the exponent?
From here, we have this formula that says k equals 0 to n minus 1, essentially is the term. And then here it's 1 minus r to the n.
Oh, okay.
So there's essentially, if you're starting out with term 0, then there would be 11 terms. And so we have to say it'd be 1 minus r to however many terms there are. So you start off with term 0, then term 1, then term 2.
So is the 9 like that you get for the answer? Is that like the sum of all the terms?
Yeah, this is the sum. This is the sum if you were to take 6 plus 2 plus 2/3 plus 2/9 plus 2/27 plus, and if I kept doing that.
Okay.
So essentially what we're saying is like all of this, whatever junk, adds up to roughly 1/3. Other questions? These are great ones. Nah? Okay. Next one. This one we can at least check out, right? Because we know we could easily list out all the terms. So it'd be like 3, then -6, then what? What would be our next one? 12, then -24, then 48, then -96. So if we wanted to add up, wait, 1, 2, 3, 4, 5, 6. Oh, I'm missing one. 192, 192. Cool. So if we wanted to, we could add these up and get like this is 96, this is 24, this is 6, and this is 3. So we'd have 9 plus 24 plus 96. So what does that give us? 129? We should get a sum of 129. Are we in agreement that we should get a term of 129? Or no? Maybe you want to fight it. No one wants to fight me? Okay. All right, so we're thinking 129 is our answer. Let's see if we're actually doing this formula right. You got a much larger answer. All right, well, we'll find out who's right here.
Wait, I multiplied by 2 and I don't know why.
What?
Because I
Oh,
did the denominator
yeah.
got 3. And then 6. Oh, never mind.
So it should be 3 times 1 minus -2 to the 7th, because there's 7 terms, over 1 plus 2. Because it's technically 1 minus 2, so that'll cancel each other out. And so this, I don't know why there's just a floating parentheses. This gives us 1 times 1, and then this is going to become positive, right? Minus a -2/7 becomes 2 to the 7th. So anyone want to guess what 2 to the 7th is? Anyone want to guess? Maybe 128? I think it's 128. Hey, guess what, gang? We got it. 128. Wow. What do we think, fam gang? We feel like we need another one to be comfortable. Is that a correct assessment of my ability to call things? Okay. Yeah, one more. All right, let's see if there's one on the next page or if it goes into something else. Oh boy. Okay, this is what we're gonna do. Try to do this one, but instead of 3 to 10, do 0 to 10. Do that. Try that out. When you got that answer, drop it in the chat. Gonna give us 30 more seconds. Should have paused the recording. This is on me. This is amateur YubTub work. All right, so our first term is 4. Then it's 1 minus 1/5 to the 11th over 1 minus 1/5. And so this becomes 4 times 1 minus 1/5 to the 11th. We're real tiny over 4/5. So this is essentially 5 times 1 minus a very small number. So we're real close to 5, right? Now, the problem is it asks for specifically 3 up. Big oofs, right? It wants 3 and above. We don't have 3 and above. We know how to find it from 0 to 10. So how could I sub this out? How could I make this from 3 to 10 and not 0 to 10? Olivia.
You subtract the sum from 0 to 3
Yeah, well, not 0 to 3.
or 0 to 2.
Yeah, we'd essentially do this. We'd say, well, if I want, this thing here, if I want from 3 to 10, and you don't even have to necessarily do 0. You could have done something else, but usually 0 is probably an easy one to do. You could also have done 1 to 10. 1 to 10 would have been fine too, but 0 to 10 sometimes. It depends on what you're asking for. But we would just do the original, which is 0 to 10 of 4 times 1/5 to the n, and we just take away what we're missing. Well, we're missing from 0 to 2. So then we could just say, all right, well, this is term 0, this is term 1, this is term 2. That's gross. So our answer would essentially be 5 minus, what even is that? I don't even, that's 24/5, 4 and 24/5, or 24/25. And so our answer is approximately 1/5 or 1/25. Wow. Wildly small. Questions, comments, concerns there?
How did you get 5 times 1 minus 1/5 to the 11th?
To the what?
How did you get 5 times 1 minus 1/5 to the 11th power?
Ah, that is me dealing with this. Essentially the 4/5 in the denominator. If I'm dividing by 4/5, I'm multiplying by 5/4.
Oh, okay.
Now, notice if we had done the same thing, but instead said, hey, I want to go from 1 to 10 instead of 0 to 1. The only thing that would change here is make this a 10 instead, right? Essentially, I'm doing it from 10 terms. And then I could just subtract this and say, hey, you're missing terms 1 and 2. Right? So as long as you kind of keep that same base, you're okay with that. And that same base kind of gets important once you get into much higher math, but you won't have to do that for many, many years. All right, try to do the second one on your own. Oh, hey, I made a diamond. That's nice. Definitely wanted to draw a diamond. All right, try the second one. Okay, so the first thing we're going to do here is we would take this as, let's deal with it as 0 to 20. And, or we could do 1. But you know what, let's let our hair down. Let's call this 1. So we're gonna do 6 times 1 minus 5/4 to the 20th over 1 minus 5/4. So this gives me a negative 1/4, or essentially a negative 24 times 1 minus 5/4 to the 20th. That's a large number. I don't know what that is, but I know this should be the only thing in print. Yeah, that would be bad. My B there, my B. So this would be negative 24 times 1 minus, I gotta throw another set of parentheses in there, 5/4 to the 20th. So I get that gigantic number. What do we think about that? Isn't it 20 instead of 21? Well, yeah, so here's 2 ways we can think about this, gang. If you want to do 21, that's fine, but then this would be from 0 to 20. So it depends on how you want to set this up. If we do it 21, again, I'm okay with that. This number becomes 2578.09. Now the problem there is that we now need to subtract. Here, we'll do it your way. We'll do your 21. Then we need to subtract what we're left with. So now we need to subtract from 0 to 3. So that would be 6 times 1 minus 5/4 to the 3rd. No, to the 4th, my bad. Over 1 minus 5/4, or essentially negative 24 times 1 minus 5/4 to the 4th. So negative 24 times 1 minus 5/4 to the 4th is minus 34.59. And that gives us 2543.5. Cool.
Mr. Erb, why
Hi.
did you why did you take the whole 6 times 1 minus 5/4 to the 20th power instead of the 21st power?
So I was changing it up. I said, why don't we just do from 1 to, instead of 0, I just was going to do it from 1 to 20, because then if I wanted to find the other terms that I'd be missing, right, I'd just be missing 1, 2, and 3. And so I could also just do that by hand, right? I'd get 30 over 4, comma 150 over 16, comma another large number over, well, that shouldn't be 116, that should just be 16. And then 64. And I could have just subtracted those manually, right? Though that's easy for me to subtract, so that's why I did it that way. Any other questions? All right, well, listen, this is where I'm at, gang. We don't have a whole lot of time left, but I got so much more math we can do. Let's really quickly talk about the sum of infinite geometric series. So if this is an infinite geometric series, that means that we have to have a couple rules in place. R has to be between 0 and 1 for it to converge, because what ends up happening is if I say like 8 times, like let's say 3/2, and I say do that an infinite amount of times, well, this just keeps getting bigger. If our number keeps getting bigger, that's a problem. We also have an issue if it's negative. If it's negative, then you're going to get like a positive number one time, a negative the next, positive, negative, positive, negative, positive, negative. It's not really a nice way to deal with or to find a sum. So the easiest way to deal with, and I think a lot of you saw that this 1 minus r to the n, if r is a fraction between 0 and 1, it ends up becoming 1, right? And so that's essentially what happens here. We say if this is 1 minus or essentially 1 times 1 over b to the n, this goes towards 1, right? The limit as n approaches infinity, as long as b is, a whole integer number, then this becomes 1. So let's look at an easy example of this. Here we're finding the sum, drawing diamonds again. Here we're finding the sum of this term starting at 0, going to infinity. It would be 4 over 1 minus 1/3, which is 4 over 2/3. So we get 6. The sum of this whole thing is 6. And a lot of times you won't even see it in that formula of a setting, right? It'll be like 4, 4/3, 4/9. Maybe they'll even throw in a 12, so you have to like figure out a little bit more that it's dividing by 3. And it'll be like dot, 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 dot. And it'll say, find the sum of this sequence, assuming that it continues forever, right? And you essentially realize that this is what it's asking for. Just wants a sum. So I think I got one for you guys to try out real quick. Oh, no, I don't. Just kidding. That was it. That was your one. All right, so let's talk about telescoping series. This is a type of infinite series utilizing the technique partial fraction, which we'll get a chance to look at here in a minute, which is a way for us to essentially use rational functions or algebraic fractions to some simpler fractions. Let's look at what would happen if we were to write this out. So let's start at the first term. This would become 1 over 1 minus a half. That's the first term. Someone tell me what the second term would look like. Anyone got the second term? This is the first term. This is term 1. So I plugged 1 in for n and got this. Plus 1/2 minus 1/3. I agree. What's the third term?
One third minus 1/4.
Yeah, what about the fourth term? We just keep plussing, and then you're going to get 1/4 minus 1/5. You guys see what's happening here? How do we see what's kind of going on? Yeah, what cancels out?
The term right before the end of the parentheses and the one right after the beginning.
Good. The term, like essentially the second part of the term, cancels out with the beginning of the next term. And so these will cancel out, these will cancel out, these will cancel out, and it keeps going. And eventually what's going to end up happening is you cancel out the 1 over n as well. And you're left with 1 minus 1 over n plus 1, which is great because we're saying, hey, let's do this for infinity, right? Let's say, what happens if this approaches infinity? What would we get? What happens if I put 1 over infinity plus 1? What does that simplify down to? No, we don't know what 1 minus infinity plus 1 is. So 1 minus 1 over infinity plus 1. What does 1 over infinity simplify down to? Nah? Questions? Just that? No, it simplifies down. Yeah, that's just 0. right? If you take 1 divided by an infinitely large number, you're going to end up with 0. So this is just 1 minus 0, which is 1. So this whole thing simplifies down to 1. Yeah, can I go over how I got there again? Sure. Essentially, do you want to go over how I got to here? Like this piece? Yeah, okay. So we realized if we put in a term like 1 over 1, it'd be 1 over 1 minus 1 plus 1, which is essentially 1 minus 1/2. Then we know we're going to add up all these terms, right? So that was the first term. The second term was 1 over 2 minus 1 over 1, or 2 plus 1. So plus 1/2 minus a third. And we keep that going. We get 1 over 3 minus 1/4. And everything starts to cancel each other out. This cancels with this cancels with this. And this will keep going all the way up until you get to essentially a plus 1 over n minus 1 over n plus 1. And so because this is like the second part of the term, or the first part of the term, it'll cancel out with the second part of the previous term. And so all of this essentially telescopes down. You get this whole big series, right? This whole, it starts like this, goes like this, you know, how the telescopes do. And then it just squishes down. And so we get 1 minus 1 over n plus 1. Well, yeah, but what's n plus 1? Well, the limit as n approaches infinity says plug infinity in for n. So 1 minus 1 over infinity is just 1 minus 0. So 1. So the sum of any telescoping series is also always 1? No, not even close. Just you wait. This is just one example of a telescoping series. Let's try the next one out. Now, for this, I want to do this as partial fraction decomposition. Now, this sounds like a very fancy word, right? This is very fancy. All this is saying is break this down into 2 fractions. Break to 2 fractions. That's all that's saying. The reason we want to do that is because we can take the limit of each and then figure out how they kind of work together. So how could I factor this denominator? How would that denominator factor out? X times x plus 1. I love it. So this is 3x plus 2 over x times x plus 1. Are we all cool with that? Cool. Now I'm saying that this must be able to be broken down into something like this. 1 over x, or a over x times b over x plus 1. We should be able to break this down into 2 separate fractions. There must be some way. So what that means is we have to figure out how that's going to work. Well, this would be x over a, or a over x times x plus 1 over x plus 1. So that's a times x plus 1 plus b over x plus 1 times x over x, right? I'm trying to get that common denominator. So plus b over x has to equal 3x plus 2. Take a second and see if you're okay with that. So in the problem, we're trying to essentially break it down into two fractions. That's it. Okay, so with that in mind, we know that essentially ax plus a plus bx has to equal 3x plus 2. So what does a have to equal? Well, a has to be 2, right? And then what's b have to be? 1. Great. That's all we're trying to do here. We essentially wanted to figure out how could we break this into two fractions. So we realized that we could take this and break it down into 2 over x plus 1 over x plus 1. Now this is one that doesn't really telescope nicely. If we were to try to find the sum, because it's adding in between each one, it's kind of difficult for us to telescope, right? Because you're just adding, nothing's going to cancel out. We want really a subtraction sign to do telescoping, so that way we find things canceling each other out. How does this useful? Oh, I don't know. Maybe in a problem such as this. Right? Who knows? Let's think about it. So how could we break down this fraction? I'm telling you that we can find the sum of this and it won't be bad. How can we factor this denominator?
You could do n plus 1 times n plus 2.
Good. So this needs to be equal to a over n plus 2 plus b over n plus 1. Right? That's how I'm going to break down this fraction here. So that means a times n plus 1 over n plus 2 times n plus 1 plus b times n plus 2 over n plus 1 times n plus 2 must be equal to -2 times, as we said, n plus 1 times n plus 2. So we can just get rid of the whole denominators. So -2 must be equal to an. Well, we can even leave it like this. A times n plus 1 plus b times n plus 2. Now, this is where we can get strategic and solve for b in other ways. If we were to plug in a specific value of n that would make this become, one of them become 0, then we can solve for the other variable. So what are values of n that we could plug in that might make this whole quantity 0? What value of n would you want to use?
-1.
Yeah, let's use -1. So if n is -1, it'd be a times -1 plus 1, which is a times 0, plus b times -1 plus 2, so just b. B is -2. That's great. All right, let's do the same thing for a. What do we want to plug in here?
-2.
Yeah, if we plug in -2, this becomes a times -2 plus 1 plus b times -2 plus -2 or 2. That's b times 0 plus -a. Oh, wrong place for that. There you go. equals -2. So A is 2. Now this is a lot easier to telescope. So this is A is 2. B is -2. Are we okay with that? Does anyone need any of that re-explained? Yeah, Olivia.
Wait, can they go together because you get those values when n is different numbers?
Yes. Yeah, that's okay. The other way we could do this is we could make a system, like multiply out the A and multiply out the B, and then you'd realize that like AN plus BN has to equal 0, and that A plus 2B has to equal -2. And then you would just like be solving for, essentially you'd get A plus B is 0, and then go from there. Does that make sense? So this is, it's easier to deal with it by essentially being cheeky and smart and plugging in numbers that make sense.
So n can be multiple values and it can still work.
Yeah.
Okay.
Yeah. And partial fraction is also very helpful in pre-calc, in calculus. I use partial fraction a decent amount. It's not just in telescoping theories. Yeah, Olivia.
Wait, but didn't you say the value was from 2 to the range was from 2 to infinity? So how can n be -1?
We're just plugging in values that n could be. If I change this to be 0, right? Or if I changed it for some reason to be like -4, that wouldn't matter, right? Like what the A and B are. This is, we're only using this because we're essentially trying to figure out like how we could make this 2 linear fractions to deal with, right? That's all this is. It doesn't matter that it's outside of our bounds of what makes sense. It's just, it's a way for us to break this down, and that's all.
Okay.
So it doesn't have to, yeah, that's a good question. It does not have to, like, because that's 2, we can be like, oh, n can only be 2 or greater, because if n were like -10, we wouldn't have an issue. But you wouldn't really do a sum from -10, but still. You could. Why not, right? All right, now, let's see how this breaks down. If we were to put a 2 in, we would get what? We get 2/4 minus 2/3. We're okay with that. That's the first term, is 2. Okay, then if we do, so that's 2, let's do 3, next term. Plus, that would be 2/5 minus 2/4. Plus, okay, 2, let's do 4 now. 2/5. No, I'm just kidding, I just did that one. 2/6 minus 2/5. What do we notice is happening here? What's going on? What's canceling out? Is anything canceling out?
The second term is canceling out with the, the first term is canceling out with the second term.
Yeah,
The next,
we're essentially having, and maybe if I had put this in the right order, right? If I had rearranged these and made it -2/n plus 1 plus 2/n plus 2, that would maybe make this a little bit easier. But we essentially realize that these terms are going to keep canceling out, right? The first term with one is going to cancel out with the second of the other. And so we realize that we're going to just be left with this extra little bit right here. So we essentially say the limit as n approaches infinity would be -2/3 minus 2/n plus 1, which is just -2/3. Now, if we were to deal with this any other way, let's look at what happens if we just do this if we just plug in numbers. If we did that, it would be -2 over 4 plus 7 plus 9. Or 4 plus, yeah, I'm just sounding. So that would be our first one, right? 4, no, that's very wrong. It'd be 4 plus 6 plus 2, so that should be 12, not 9. Right, which is what that adds up to. And then we put in 3. So it'd be 9 plus 9 plus 2, so -2 over 20. And then we do it again, we get -2 over 30. And we do it again and again and again and again. And it's hard to see a pattern here, right? That's not really a nice pattern to deal with. The only thing we'd be able to say is that this pattern has something going on with the denominators and the numerator always stays negative. We would not see the canceling out unless we break it down into this partial fraction decomposition. Break it into 2 separate fractions and see how stuff cancels out. And there you go. All right, well, hey,